CCAN webinars. We're very pleased to have you all join us. We're hoping this will be a successful program. As I mentioned, this is the first of what will hopefully be quarterly CCAN webinars. For those of you who are new to the webinars, if you look at the right side of your screen, you will see a place that has opportunity for chat. If you're having any difficulties hearing this presentation, if you're having any difficulties seeing the slides, use the chat button, and there is somebody standing by to try and help you with that. If you have any questions as you hear the webinar, you'll also see a questions box to the right. Please go ahead and make use of that. List your questions. Because of the difficulty with so many people online, we'll end up reading your question for you. So go ahead and write it there, and we'll give you a reminder to do that as we get closer to the end of the segment of the webinar. So with that, I'd like to begin, and I'd like to do that by introducing what is CCAN. For those, I think most of you will be aware of CCAN because you probably got the notification for this webinar through the CCAN listserver, but for those who are not, CCAN is the California Current Acidification Network. That is an informal partnership that developed between the science, management, and industry, mostly the shellfish industry, serving to collaborate and look for ways that we could build off of each other to enhance our understanding and the management of coastal acidification. It began in 2010 with a workshop that brought together these different sectors and realizing that there's a lot to be gained from each other. And I think that's something that has happened to a great degree. The scientists in particular have gained a lot of perspective on what the questions are by working with industry and identifying the kinds of decisions that they and the water quality managers need to make. It's helped drive the science, and then of course in turn it's led to a wonderful amount of science that has then come back to the industry and to the larger management community that's helped drive a lot of the decisions they make. So with that, our next slide describes the four kinds of products that CCAN has produced to date. We've had a number of workshops that have led to these products. The first is a CCAN vision document, and that's what we put together initially, identifying why we come together, what we're trying to achieve. And a part of that was identifying that we wanted a West Coast monitoring network, that there were a lot of people who were taking measurements. Let's find ways to take them together, and as I'm sure many of you are aware, a lot of that monitoring is actually now going on at industry sites. And so the merging of the scientists and the industry towards a common goal has been wonderful. The second document was a core monitoring principles document. If we want a monitoring network, what are the kinds of things that we're going to measure in that? And there were a number of things that came out of that core monitoring principles document, but the one that's most relevant today is the idea that we needed a common currency, things that we're all going to try and measure together. And as part of that, the idea of a aragonite saturation state as that currency, something that allows you to describe the entire carbonate system, but also something that provides a common currency, came out of that, and that has been one of the things that's really been adopted by the larger scientific community and even the larger monitoring community, as what we've done in CCAN has expanded to group K areas and things like GOAN. The third document we came out with is if you're going to measure aragonite saturation state, you need to measure two carbon-based parameters to do it, but there's a suite of potential carbon-based parameters that you could measure. And so we provided some guidance on knowing what the technologies are, knowing what the quality of the measurement techniques within those measurement types are. We developed a series of guidances on how you would go about, what parameters you would actually measure. Which leads us to the document we'll be talking about today, because one of the things that came out in that guidance document is for continuous measurements, the FET sensors for measuring pH are one of the key pieces to how we would go about setting up this monitoring network. But as Andrew Dixon likes to say, when you go to buy this, they don't come with a lot of operating instructions. And so what we want to do is find practices that we can agree upon as a network that we'll try and deploy as we move forward so that we can enhance comparability among groups that are doing the monitoring, and particularly when they're using the same sensor, in this case, the Durafet sensor. Which now leads me to introducing our speaker for today. We're very pleased to have with us as our speaker Dr. Todd Martz. Todd is a marine chemist at the Scripps Institution of Oceanography, but more than that, when you go and think about who is the top person in instrumentation measurements for ocean acidification, if Todd isn't on the top, he's certainly not going to be past the first handful. He just has really been one of the people who has developed the whole FET sensor and has been moving it from just the tabletop versions to employing them in larger types of equipments that are autonomous instrumentation, such as floats and moorings. Todd also deploys this instrument to study biogeochemical processes in the ocean. So we're very pleased to have with us today Todd, who will tell us what are the 10 best practices for implementing a Durafet sensor. And with that, Todd.
Thanks, Steve. Hold on a second. Let me just get my presentation going here. Okay, do you guys see that?
Yep.
Okay. Well, I'd like to thank Steve and the CCAN steering committee for inviting me to give this presentation today. In this title slide, what we're looking at is a number of photos from different deployment locations, mostly around California, but also around the world, carried out by my lab and also other collaborators. The CCAN audience, I know, consists of people interested in both autonomous and underway type measurements. So I'll talk a little bit about both of those, but most of my work is focused on the autonomous version of the Durafet in the sense of something that's left out in the ocean logging on its own batteries. But there's, you can see the upper right-hand picture here is an underway type setup, which I know is of interest to many people, like Benoit, who is also on the panel today. So just a quick overview of what I wanted to cover. The basic topics are going to follow this this document, two documents really that we've worked on over the last couple of years. Phil Bresnahan and I published a paper in Methods in Oceanography last year, and that paper was sort of redacted into a shorter version that was recently posted by CCAN. So these two documents cover most of the same topics, but the document you see on the right, the CCAN document, is a little bit less technical. So that was the goal. One of Steve's goals was to make it a little bit more readable by non-experts. And throughout this presentation, I'll touch on various OA technology, a little bit outside of pH sensors, but try to focus mostly on the Durafet work. But I've been thinking also about OA technology at large, and so I wanted to maybe touch on that a little bit. So the outline for this presentation essentially will just follow the recommended protocol. So I just want to show that up front. This is basically the 10 different topics that Steve mentioned that has come out of these two documents, and we'll just kind of step through these mostly in this order. And I want to just point out that this really is specific to the CFET sensors that we've been working with for autonomous deployments. But a lot of these can be extended to underway type measurements, but these were developed based on our experience with autonomous Durafet-based instruments. So just a couple of background slides on this for those that aren't familiar. I started testing the Durafet when I was working with Ken Johnson up at Mbari, and the first field data with the Durafet were collected back in 2007, actually in an underway system alongside a PCO2 system. So the first measurements that we ever did were actually underway, but then our focus was always to turn it into an autonomous system, and so we immediately after that developed the CFET, and that was since refined at Scripps after I came here a little over 6 years ago, and eventually commercialized by Satlantic. And along that same line, we developed in 2010 what we call the CFOX, and the CFOX is essentially the same component as the CFET with additional auxiliary systems, namely a CTD, or a conductivity temperature sensor to measure salinity, along with a Siebert pump. And these are plumbed into a flow cell, which also includes, in addition to the pH system, an oxygen sensor. And recently we've also been sort of modifying CFOX to do different measurements on mobile platforms like wave gliders and stand-up paddleboards. And this is really Phil Bresnahan's work, but Phil's worked on this other thing called the WaveFox that most of you have probably never seen. And I also want to point out that there are many other groups now building Durafet-based pH data loggers completely independent of this CFET family of sensors that I just showed you. So Gretchen Hoffman has provided a figure last year sometime showing, this is the lower left-hand figure showing the various Durafet-based sensors operated by University of California researchers. A few of these are CFETs, but a lot of these are systems built by Gernot Friedrich at Mbari, and this is independent of the CFET. And those systems are also deployed not just within the University of California, but within the Omega's science program, which you see on the figure at the right. And presumably they're deployed, and maybe other types of systems are deployed within the global ocean acidification observing network. And in terms of the go-on sensors, I'm not very familiar with how many Durafets are operating out there, but I think it's safe to say there are hundreds of Durafet sensors operating in these various networks, just based on the fact that my lab is built over 100. And in terms of underway systems or laboratory-based systems, NOAA has installed a number of CFET configured for underway that were built in my lab. There are many ocean acidification researchers. For example, the environmental lab at Friday Harbor is operating Durafets and mesocosms. Here they have, I think, 12. I just grabbed this photo off the web showing all this gray box is the off-the-shelf Honeywell analyzer for the Durafet. And there are other measurement systems kind of coming online now that would be considered multi-parameter. So maybe the best example that people within CCAN are familiar with is the Berkelator system, which does a PCO2 and a TCO2 or a DIC measurement. And I believe some of these systems are now configured with Durafet sensors as well. And we've done, like our early work back in 2007, we have pH TCO2 systems. There's one just about to go out on the next Cal Coffee cruise right now. So that's what you're looking at here in the lower figure. So just to give you a taste of the data that have come back from these, this is the very first pH Durafet data from work at sea, and this is the underway data that we published in 2010 from the 2007 cruise. And what I'm showing here is just sort of one of the benefits of collecting multiple parameters, is that you can combine them to get a third parameter. In this case, we were combining pH and PCO2 data to get total CO2, shown on the right. But we also had a third measurement. We had a total CO2 measurement in this case, so we can compare how well they agree, and we can see that when we combine certain parameters, there may be some things that we have to worry about in terms of how errors propagate and how well we can actually resolve a total CO2 measurement from pH and PCO2. And the last thing, just kind of introducing sensors, that I want to point out is that there are a lot of commercially available instruments out there. There are also a lot of gaps. So one of the things that I kind of want to get across here is that there's still some work to be done, and even in the Durafet area, there's work to be done. This chart is in an Oceanography special issue coming out in the next few months, and it categorizes the different pH, the different master variables of the CO2 system, including pH, by level of autonomy. And one thing that you'll notice here is that I don't list the Honeywell Durafet as an underway system. And the reason for that is that it really is not supplied by the manufacturer with any sort of automation or sample processing specific to pH, to seawater pH. And that the lack of seawater specific pH data processing in an automated system, that's what's cutting most sensors out of this chart. But you can see the CFET and the SAMI and the under sunburst system are all listed under pH because these do produce a number that represents a seawater pH value. And the last thing that I wanted to just mention that has led to this set of best practices is that we completed a first of probably more sensor workshops this last summer at Scripps, where we had a group of people come out and get hands-on training with Durafet-based, and also there were a couple of SAMI systems there. So we had a week to do deployments and collect bottle samples and try to actually apply the bottle sample corrections to the data and fun things like that. So back to the recommended protocols list, starting with this first one, and this is, again, specific really to CFET-based systems, but we find that it's extremely helpful to operate these sensors before the actual field work begins. So in terms of a condition, we would call it a conditioning period, to just operate sensors in natural seawater to condition, and also to test them shoreside before deploying them in the ocean or deploying them in whatever test system you're using. And this figure out of the two papers summarizes a number of problems, and the first one that's outlined here in red is the conditioning period. So this is why we recommend conditioning Durafet systems. And the one thing I'd like to point out that does get a little bit technical is that there are two different lines here with completely different conditioning periods. And if you look at the black line, this is the Durafet signal based on its internal reference electrode, and the blue line is the Durafet signal using this external reference sensor that we integrate into the CFET and CFOX. Clearly the blue line has a much longer conditioning period, and the black line has a very short rapid conditioning period that's associated with the liquid junction of the internal reference conditioning to seawater. So it helps to understand a little bit about the technical aspect of what's conditioning. And if you're using, for example, a sensor that doesn't have an external reference electrode, you might not have to worry about allowing a 1-week conditioning period. Or you might hope that the manufacturer had done it, but you'd want to know either way whether or not you need to condition, because this applies later when you go back to quality control the data based on discrete samples, which is the second recommended protocol. So we always recommend collecting the second recommended protocol, is collecting shoreside calibration points, and then collecting some in situ samples during the period. So sorry, this bullet here doesn't apply completely to this graph, but we really want to, after the thing is deployed, collect some sort of in situ data point alongside a sensor. So this is one of the recommended protocols, is to get at minimum one data point, which is number 5, take practical, frequent, discrete samples. And one of the other important points to make about this is that you want to do it after the sensor is conditioned. So there's a lot happening in this graph, but one of the points to make is that if you take a sample right at the point when a sensor is deployed and it hasn't conditioned yet versus a sample after the sensor has been operating for a while, you can expect maybe to obtain different results if you're using just a single point to correct your time series. In terms of biofouling, I think most people recognize biofouling as maybe the biggest problem when we're working in the autonomous environment. But so we're leaving a sensor out for weeks to months. Biofouling is one of the biggest, if not the biggest, problems that we have to deal with. And so here we have a number of recommendations for minimizing biofouling. You can never completely eliminate biofouling. It's kind of an interesting, or it's an important point to make, is that you can never fully eliminate it. You kind of have to live with it, but what can you do to minimize it? So these are some of the things that we recommend using a flushed flow scheme. So this is really the progression from the CFET to the CFOX. Is one of the things that we decided to do is, instead of using passively flushed copper screens, use a flushed flow cell. And incorporated into that flow stream is a Seabird instrument, which is number 2 here under the 4th recommendation. Seabird CTDs are typically equipped with a tributyl tin biocide plug, and by adding that into the flow stream of your other sensors, you can really cut down on biofouling. You can also do things like wrap the sensors in tape and paint them with anti-fouling paint. This may help improve the data quality, but it's also partly done as a matter of convenience to help save on cleanup afterward. Ken Johnson has been using, and also the mooring group for many years at MBARI, has been using a 70-30 copper-nickel alloy around sensors that have seawater intake. This particular material was selected, I believe, for the PCO2 systems on the MBARI moorings, and then they started using it around Durafet sensors. So we think some people will just use regular copper, but it seems that the copper-nickel alloy actually works a little bit better. So one point to make in terms of the biofouling is that it's difficult sometimes to actually identify biofouling, and so some of the protocols apply to each other and overlap. But in this case, it would be possible to identify the biofouling if you had enough discrete samples. But one of the other recommended protocols is to deploy multiple co-located sensors, and by looking at the deviations between those, you can immediately identify the onset of biofouling much easier than you could with a series of discrete samples. And so what we're looking at in this figure is the deviation in the upper right, deviation between two sensors, one of which is not fouling and the other is fouling. And of course, when you get up to an error in pH of 0.5, it should become pretty obvious there, even based on discrete samples. But what we'd like to do is identify the very onset of biofouling at the 0.05 pH level. And in order to do that, it's extremely helpful to have co-located sensors deployed. This is the same time series of pH anomalies for 4 different sensors located on this mooring. This is in Monterey Bay on a Lobo mooring. And one point to make here is just that we see these decreases in pH due to fouling, and you can demonstrate that this is fouling by going out and cleaning the sensor, and it comes back to the right value. So fouling, cleaning, and this is some of the implications here are that if you can identify it, you can go out and address the problem depending on how close it is to shore. So in the case of an underway system, we may not have to worry as much, or we may not have to put quite as much effort into thinking up new ways of biofouling prevention, because we can address it by cleaning the system on a regular basis. I want to spend a little bit of time talking about these recommended protocols of taking when practical, take as many discrete samples as possible, because this is kind of the first intuitive thing that people would do to validate in situ systems. You would naturally think, well, we should go take bottle samples, and you'd be right. You should take as many bottle samples as possible in order to quality control your data set. So that's what we're looking at in this bottom figure. This anomaly is the plot generated when you go out and take frequent bottle samples. And what we recommend is to make 2 different plots. So that's this recommendation number 8 is to assess and quality control the pH sensor data using what we call a time series anomaly plot or a property plot, also sometimes called a cross plot. So these two plots can be extremely helpful in data quality control. The first thing that you would do with an anomaly plot, the time series anomaly plot on the left, is look for obvious errors in terms of sensor drift, like the biofouling problem, and then eliminate that data, or possibly drift correct it if you're feeling ambitious. But we don't always recommend drift correcting sensor data. In my opinion, correcting bad data, it's very hard to come up with good data. It's normally better to throw out the bad data altogether. But maybe that's a discussion topic. It is, like I say, it's a matter of opinion, I think. Once you've quality controlled it in an anomaly plot sense, you can sometimes apply a correction to the calibration in post-processing using some type of a property plot. What we're looking at on the right is a sensor versus bottle measurement property plot, and doing a simple regression through it. You could, for example, use a slope and intercept to correct the sensor data to come into agreement with the bottle data. Okay, so this sort of raises the question of how well should the bottle samples agree with the in situ sensor data. We've been doing this for a long time. Others were doing this before us. I mean, ever since people have been putting CTDs in the ocean, they've been going out and trying to measuring bottle samples of salinity and then comparing it. Here's a data set from 15 years ago where we had SAMI pH in a river and took 16 bottle measurements alongside it. The typical thing that you would do with this data set is look at what we would call the relative accuracy and the standard deviation of the residual plot. So the relative accuracy value is going to tell you something about of the overall quality of your calibration, and you could imagine applying a simple offset to that value in order to bring a sensor into agreement with your bottle samples. There's another really important number here, though, the standard deviation of the residual. This reflects how well you're doing in terms of your spatiotemporal mismatch or added in bottle measurement errors. We typically assume that our bottle measurement errors are relatively small compared to the spatiotemporal mismatch issue. So in this case, we were achieving a standard deviation in the residual. The RMSE is the same, calculated the same way, of 0.004 pH. So that would be, maybe that would be a benchmark how well you could do with bottle samples. But it turns out that it's really, I think in a lot of cases, it's dependent on the sampling, the environment that you're operating in. So if you're in a highly dynamic environment with very strong pH gradients, you could expect to do for things to be much more challenging to bring your bottles into agreement with your sensors, just in terms of nailing down a timestamp and time and space. Are you measuring that water that's in contact with your sensor? And this is kind of an interesting table, I think, from a few different examples collected over the years. The first line in this table is not based on bottle measurements. This is really the best you could ever possibly hope to do. This is a case where you have an autonomous sensor operating on a mooring, and you took a ship out and you sat right next to it for a period of time. You averaged your data as much as you wanted to, and you just really nailed down the PCO2. If you convert that PCO2 that Benoit measured in 1995 into a pH value, you'd come up with a RMSE of like 0.0007 between the 6 values that they had, which is just better than anyone that I know has ever done with bottle measurements. Phil's paper that just came out, we had 12 bottles and were able to report a number of 0.002, and this was based on measurements that Ken Johnson's group collected next to the L20 mooring where we saw those data earlier with the biofouling curves. That was the L20 data. So we know that we can get into the third decimal place based on bottle samples. That previous slide that I showed you, the SAMI pH in a river, we were into the third decimal place at 0.004. And at Ocean Reef, Sarah Cullison, working with Mike DeGrand for SAMI, also got 0.008. And I wanted to mention that now there's a bunch of data that have just been released by the Alliance for Coastal Technologies, and I just plucked a couple of numbers out of that, but their test for the CFET, and now we're seeing people are really doing a good job of making a lot of bottle measurements, which is nice because now we have ends of 100 or 80 through this work that ACT has carried out. And there are a few examples in the ACT test where they got 0.007 or around there. And a lot of the ACT data, though, it seems that they were up higher at more like the 0.02 or higher range, which raises some questions. And I'm not sure. I'd be interested to understand why those numbers are higher than these previous values that we've seen. One thing, I guess, to point out, I've just had a chance to look at this over the weekend. ACT did report a number of the 0.003 for the SAMI, shown here on the right, plus minus 0.003, but I believe it's a typo when I look at their figure. I think it's actually 0.03. So the CFET is at 0.03 in that same figure. These scales aren't quite the same, but I think this really raises some questions and maybe hopefully generate some discussion about how to do the best possible job aligning discrete samples with sensor data, because I think it's great that we're going out and collecting 80 or 100 samples, but why have we gone from the third decimal place into the second decimal place in terms of the RMSE value? It may actually come down to a simple data processing issue, like neglecting to properly interpolate data, or assuming that just sample timing is all that you have to do when you may actually need to interpolate timestamps. So one of the other recommended protocols involves deploying co-located independent sensors, and this is one of the hardest things for people to implement. We still recommend it as a best practice, but we do recognize that now we're talking about a very expensive instrument suite when we say you need to not only deploy your pH, but PCO2 and oxygen sensors in addition. But this does afford much more information. For example, number 7, you can then estimate pH from these empirical relationships, which is what we commonly do when we're running through the quality control procedure. And so now when you have a co-located sensor and you look at these cross plots, you get much richer data set, and you can still do the same types of comparisons as you would with, say, 12 bottle samples, or at best, anyone getting up into the 50s or 60s in terms of bottle samples really has a good measurement program set up. Most people I'd expect aren't actually achieving that many bottle samples for a single deployment. But the co-located sensors allow you to do things that you just would not normally be able to do based on purely on a series of bottle samples. So this busy figure that I showed before, one other thing to mention here is that this green value is pH that's been predicted based on oxygen using Simone Allen's equations that they published a few years ago. So you can transform oxygen in certain locations below the euphotic zone into a pH value, and then you can compare that in an anomaly plot, and things will jump out at you. You can actually see an instrument drifting, for example, and you could convince yourself based on this data set that one of the reference electrodes failed and that the other one continued to work, and now you have a quality control pH data set. So I want to touch on just a couple of other things before I run out of time, things that we included in Phil's paper. And this might be a number 11. I didn't run through these. I know I didn't run through these in exact order, but number 9 and number 10 sort of go along with everything that I've just been talking about. I'll just mention briefly number 9, where we say apply a single calibration point. This could mean literally a single bottle sample or some sort of an average based on a number of bottle samples. The real thing, the point that I want to drive home about number 9 here is that we don't recommend forcing sensor data to agree with multiple individual bottle samples, okay? Because when you do that, you're essentially imparting a sampling error from the bottle samples into your sensor time series, if that makes sense. In terms of pressure response, maybe we should have included this as a recommendation, and maybe that's the good thing about having a CCAN document is that it can evolve, and we can include additional corrections or added recommendations. But I never recommend pressure cycling the off-the-shelf Honeywell Durafet sensor because of the data that we see here. And this shows the pressure response of 2 different Durafet sensors with 2 different reference electrodes. So each sensor with 2 independent reference electrodes. So the short story here is that we see a different pressure response for each sensor, and we've also seen it to be hysteretic. And since at this point no one is regularly systematically characterizing the pressure effect on the stock Durafet sensor, it's not a good idea to use them for pressure cycling in the sense of carrying out ocean profiles. Even though the sensors can operate up to 70 meters, it's not recommended to take a Durafet sensor and do 0 to 70 meter profiles with it. And it may be in the future that if you go out and you carefully collected these types of pressure response curves that you could do this, but my feeling is that by the time that you figured out how to do that and really established a protocol for it, a pressure tolerant version of the Durafet will be available. Another question that we often get asked is in regard to salinity, and the answer here is probably not going to make everyone completely satisfied, but we really, the short story is we've not tested CFET type sensors over the full range of salinity for a variety of reasons, absence of standards mostly, but we have tested it down to a salinity of 30, which is what you're seeing in this figure, and that the data here led us to conclude that in the salinity range of 36 to 30, we do not need to apply a salinity correction to the pH value based on the internal reference electrode. We've always known that we have to apply a salinity correction to the pH based on the external reference electrode. And you can see, for example, if you look at this green line in the bottom, this would be the deviation in the pH value in the external reference electrode-based pH if you don't salinity correct it. So these are huge, huge errors for CCAN folks trying to characterize saturation state. These would be unacceptable errors. So if you do apply the understood salinity correction, you get agreement within, when everything's working, the 2 sensors in a CFET agree to better than 0.005. This value, I would point out, in the lower right could be of use to some people just as sort of a number to stick in the back of your head, because in some cases, if you had a CFET from Satlantic, which does not have its own salinity measurement, you'd like to know, well, how sensitive is it? That's a very well-known number. It's going to change by 0.013 pH per salinity. And so if you know a little bit about your deployment location, if you know the salinity is stable to X, you could use this simple number to tell yourself whether or not it would be acceptable to operate that sensor in the absence of a salinity measurement. Steve, how am I doing on time right now? see. I feel like I should end on.
We're actually running a few minutes long. You could finish up in the next 2 or 3 minutes.
Yeah, I think
so we
that.
then one questions. That would be.
Why don't I skip that slide and I'll show just these. This is last two. I'm just going to mention two more things. That in this document we had two notes, one on pH scales, and this is just sort of a matter of convenience, and we'll post these slides so you could read this later, but I chose just to include this for non-experts, simplify conversions between pH scales, and there are also maybe one of the most useful parts of this document is note number 2, which contains MATLAB functions for data processing, and we know that this has been very helpful to a number of people. So I think that I'm happy to end there, Steve. Sorry for running a couple of minutes long, but maybe we can take questions or hear from Benoit.
Outstanding. Thank you very much, Todd. So what we're going to be doing with this webinar and with all the other CCAN webinars is get a perspective on whatever the talk is from both the scientist side and from the industry side. And so towards that end, we have recruited Benoit Eudeline to give us the industry perspective. Benoit is the Division Manager for Research and Technology for Taylor Shellfish and has had extensive experience deploying Durafet sensors. And he's one of those rare individuals who has both a science background, having gotten a PhD in this field in France, and having come over to work at both the Whisky Creek Hatchery and the Taylor Hatchery. And he's going to give his perspective on what it's been like using the Durafet sensors and how he has started to use some of the recommendations that Todd has put forward, and whether he's finding those to be practical and useful. So with that, Benoit, would you please give us some perspective?
Thanks, Steve and Todd, for this presentation. So yeah, today I'm going to talk to you guys about our experience with the Durafet pH probe in the shellfish industry. We have been using this for about 4 years now, and all of them are deployed in commercially important bays for the shellfish industry, either as standalone units to monitor pH and water quality, or often coupled with percolator, as Todd mentioned, PCO2 or PCO2-TCO2 carbonate chemistry analyzer. We are also using them at the Taylor Hatchery to control our carbonate injection system through a PID loop control. So, these numbers are changing, but I would estimate we have about 10 Durafet sensors deployed throughout our industry. And most of them are available online. The data are available online through the IUS network, which is, the goal. It's for our growers to be able to look at the data and act upon them. It is important to note that we are using, in I would say most, if not all places, commercially available packages. So they include the Durafet 3 probes with internal references and UDA 2182 analyzers. So, we are not dealing with raw voltages or MATLAB. It's all the commercially available versions. And again, they are used in estuarine type environment where there are lots of temperature, salinity fluctuation, and lots of biofouling, which is probably one of our main problems. But this being said, overall, our experience with this probe has been very positive. We have had there basically a piece of electronic, so we have had our occasional malfunctioning probe, and generally we know when this happens right away because, the pH data are either wrong or very unstable, and the probes are hard to calibrate. So when we get one of these, we just return it. But again, for the most part, they have been very reliable for us, and we generally use them for about a year, at least in our facility. Because of the internal reference electrode and the gel, we feel like there is a risk of contamination of this gel. So after a year, we generally replace them. And during this 1 year period we have had of usage per probe, we have had very little failure. As a commercial user, I would say that probably the main attraction to us, besides all the points that Todd mentioned and the overall data quality, has been the low drift compared to classic glass electrode, which is very important for us. As you can imagine, some of them are deployed in remote locations where we cannot service them very frequently. You might be able to get, I know we have MD Serby here at PSI, Pacific Shellfish Institute, servicing some of our probes. And he might not be able to get to the probes always in a timely manner, but he might be able to have somebody there on site clean the probe. And so it's always a good thing to know that as long as you can keep the probe clean and free of biofouling, the pH data can be collected for several months without significant drop in quality. This being said, and it's not really based on much data, but we try to calibrate our probes at least once a month in our hatchery, and we do clean them up to several times a week to maintain data quality depending on how much fouling is in the water. I'd like to address another point that Todd mentioned about discrete sampling and co-located sensors. And it was a very important point that Todd made about discrete sampling and how close can you be to your probe when you take this discrete sample. And I think that's probably one of the challenges we are having in our location, because the water quality can fluctuate quite fast at times, and again, collecting a discrete sample can be quite challenging, and to make sure that you have the same water that the probe is measuring. But this being said, we do collect discrete sample where we measure so that we can measure carbonate data and use the calculated pH to validate the Durafet measurements. And although there is a significant cost associated with this sampling, we do this on a weekly basis at most of our sites where we have a Durafet deployed. And we feel like it's important to do so and ensure good data quality and data validation. This being said, as you can imagine, there is a significant time delay between collection and analysis of these samples. And so it really cannot be used as a live way of ensuring data quality. But in many of our locations, these Durafet probes are being coupled with a percolator or even the percolator deluxe, like in our hatchery and a few others. And what is the percolator deluxe? It's basically a carbonate, it's an analyzer which provides live carbonate chemistry, and every hour does a DIC measurement on our seawater by acidifying the seawater sample, and of course it also measures the PCO2 as well as salinity, temperature. And so this results in an accurate calculation of the carbonate chemistry parameters, including pH. So in effect, you could say that we are analyzing 24 discrete samples a day in our locations. And these are displayed on screen, on the computer screen, and compared to the Durafet measurements, made on the exact same water. So this for us is a very great tool, and we use it literally on a daily basis. We are looking at the data generated by the discrete sampling compared to the continuous Durafet measurement. And although we are just right now starting a collaboration with Jeff Lebon and Simon Allen at NOAA PMEL, we are starting to basically the data quality validation process for both accuracy and precision generated by this machine. So I cannot talk too much about this accuracy and precision, but all I can say is that at the moment, when we look at the calculated pH compared to the measured pH for the Durafet, they are generally very close to each other and within 0.02 if all the conditions are right. And that's a key point, because at times there is a much bigger difference than that between the calculated and measured, which is a sign for us that something is wrong. And as Todd mentioned, generally it has to do with biofouling, so that's a very good indicator for us. And as for collocated sensors, These Durafet probes are generally run in parallel with a seabird thermosalinograph and oxygen sensors, and this for us is also can help us understanding and troubleshooting sudden water quality changes. You know, it's not uncommon for the pH to drop 0.5 pH unit in a few hours. So when you see that, it's always quite comforting to see that the salinity and temperature and oxygen level change accordingly, which tells you that it's probably true data. And finally, I'd like to kind of give a couple points that we have learned over the years and about the Durafet probes. And the first one is about temperature compensation. I think it's important to note that for a commercial user like us, that the temperature probe used for temperature compensation and measurement is located inside the body of the probe itself, about 1 inch above the FET sensor, and which basically means that the temperature is slow to respond to temperature changes. And although the tip of the probe is threaded with a 3/4 inch thread, the regular pipe thread, which means that it's really enticing if you want to, when you want to have inline measurement, it would be very easy to just screw the probe into a 3/4 inch T, for example. We don't recommend that, because what happens is that really the probe is not submerged in the liquid to be measured, and really you would be temperature compensating with the temperature of the room instead of the temperature of the liquid. And even Honeywell in their manual stipulates that the probe should be submerged in the liquid to measure for accurate temperature compensation. So for our inline applications, we use a sleeve, basically a rubber sleeve that we can introduce the probe through, and so that the probe is immersed into the liquid to measure. And it has an impact too on calibration, because just for the same reason, when you are calibrating the probe, you need to make sure that the probe gets equilibrated to the buffer temperature. For this reason, we generally calibrate with buffers cooled down to the temperatures to have the buffers and the probe cooled down at the same temperature, and ideally to avoid temperature compensations error. We also make sure that we calibrate the probe at the same temperatures at which the probe will be used to measure pH. In other words, in summer we might calibrate the probes at 20 degrees. In winter we might calibrate them at 5 degrees C based on the ambient temperature. And finally, and I know this has been always for us a big challenge, calibration, and Todd mentioned about the 1-point calibration, and so far we have not been doing that. Despite their low drift over time, as I mentioned, we calibrate the probes once a month, and initially we were told to use 2 saltwater buffers to calibrate this probe, one trace buffer and one AMP buffer. But we quickly realized that since we were using the UDA2182, this was not possible, because basically you get an error message telling you that the span between the 2 buffers is too small, and so that it cannot calibrate. So then we had to go to a more traditional calibration technique using regular freshwater NIST buffer. And we do this to establish a slope, and I'm not even quite sure if it's a proper way, and then we calibrate the probe. So this calibrates the probe, what we call NBS scale, and then we apply an offset with a sample cal on the UDA2182 using a trace saltwater buffer, and this shifts the probe to a total scale. And again, this step for us can be a problem, because sometimes when we do this shift, we observe the expected about 0.15, 0.17 pH drift. In other words, when you switch from the NBS to the total scale, the pH goes down, which is expected. But sometimes I have to acknowledge that sometimes when we run the NBS, the trace buffer, and the probe is calibrated in NBS scale, when you run the trace buffer, the probe reads already the right pH expected And so basically there is no offset applied. And so this for us is quite challenging, and I know Todd will have a lot to say about this calibration process. And that's what I have to say. I mean, in general, you know, again, we are very happy with the Durafet probe, and these probes are quite accurate, and we like them, and we are using them a lot. Thank you.
Thank you, Benoit, for that perspective, and not just perspective on the Durafet sensor as a whole, but which of those recommendations that Todd has been putting forward you've found useful and which ones you might be using in the future. We want to use the last 5 or 10 minutes, and we're willing to go over if people are willing to stay, to answer questions. You all are in listen mode, but there is on the right side a box for asking questions, and we'll proceed to answer those questions. Joining us in answering those questions will be Phil Bresnick. Phil is one of the authors of the paper on which the 10 principles that Todd put forward were based on. The first question had to do with availability of this presentation. The presentation itself will be placed on the CCAN website, and our next slide actually shows the website, as well as the PDF behind that, so feel free to share that with others. In terms of technical questions, Todd, I'm hoping you're back on the line because the first one is for you, and it actually came from 2 different people. They want to know a little bit more about the difference between the internal and external reference electrodes and how you would use them.
Okay. Well, you know, couple of the figures I showed indicate that when all things are working properly, you get essentially the same value from both of those electrodes. So why do we add the external reference electrode to the standard Durafet? The first answer is for redundancy, because half of your measurement is your reference electrode, and it does add additional information to the system. I tend to think of it as we have 1.5 pH measurements, because although we have a single pH sensor, 2 independent reference electrodes can give us an indication when something is going wrong in the system. And that the other reason is that in thinking into future applications in terms of both long-term deployments when we were first starting out building the CFET, and then eventually trying to do high-pressure applications, we always wanted to get away from the internal reference electrode, because the liquid junction associated with the internal reference electrode, this element of a reference electrode is notoriously problematic in terms of reproducibility, pressure hysteresis. The external reference electrode is a junctionless electrode. When you combine it with the ISFET, it's a junctionless cell. So those are the 2 reasons. And Steve, if I could just jump back and just say one more thing about just back on when Benoit was finishing up on a point that I would have made in my presentation in regard to the UDA analyzers, is that I think it's really important to follow up on the work that's already been done in best practices, and we still have a ways to go in terms of generating some protocols for how oceanographers can use the stock Honeywell components. There's not a thoroughly documented set of protocols for how do you measure seawater pH with the UDA analyzer, and that this is something that the community needs to address.
Thanks, Todd. The next question, which we actually had from several people, is can you discuss a little bit about the cleaning procedures? And people want to know, how do you do the manual cleaning? Somebody even asked, should I just be using a toothbrush?
But you can get in there and do some scrubbing right on the sensor. I don't know, if I would recommend taking a toothbrush right to the surface of the FET, but we would one procedure that we've used is pushing hydrochloric, like 10% hydrochloric acid through the cell, letting it sit. That will generally kill stuff, and then followed by flushing it, you can move some of the junk out of the cell. The ideal procedure is to be able to do a swap, and then have the dirty sensor back in your lab for lab-based cleaning, where you can actually in our case, we would want to take the Durafet sensing, the sensor itself out of a CFET and go through a procedure where we probably soak it in some acid, gently clean it up with chem wipes and things like that. That said, anytime we get an opportunity to have a CFET in our lab, we generally throw away the Durafet and put in a new one.
Okay. Next question, again, asked by two people, is you talked a little bit about the sensors being tied to pressure change, cycling of pressure, but you didn't say much about the variability or the changing cycles of salinity. Can you talk a little bit more about how responsive they are to that and what kind of advances you see in the future for using them in that kind of environment, and particularly in lower salinity environments?
Sure. Well, there were two slides in that presentation. One was on pressure and one was on salinity. The main number of interest for the salinity slide was that number in the lower right-hand corner of the screen that was the 0.013 pH unit per salinity. That applies to the external reference electrode only, and so that you should. The essence of that slide is that over the salinity range that we've actually tested, we don't have the data to justify applying a salinity correction to the pH based on the internal reference electrode, and we are applying a understood and appropriate correction to the external reference electrode. Beyond that, going to lower salinities, this is the second thing that I would lump two things into the the statement of what needs to be done next. One, develop some standard protocols for using UDA analyzers and in seawater. The other one is someone needs to do the work to establish calibration protocols for these sensors at low salinity, and neither of those have been done so far. So in terms of commenting on how do you operate at low salinity, I mean, I really have to just stay silent on that because we haven't collected the data to actually be able to recommend protocols at operating the system. So I don't know what's the lowest limit of salinity where you can, and then at what magnitude of errors could you expect to see. I will say, and I didn't show this in my slides, there is some new information in the new the Alliance for Coastal Technology reports with testing various sensors at low salinities.
Thanks. So we've actually reached our time limit, but we still have most of the people who attended online. We can stay online to continue answering questions. We have about another half dozen questions to go, so I'll just keep going if people need to leave. I thank you for your time. I in particular thank Todd and Benoit as our presenters, and I want to also make sure to recognize the NOAA Ocean Acidification Program and Jennifer Mintz, who is essentially the engine behind making these webinars work. Continuing with the questions, Todd, can you share the MATLAB files that you referenced?
Yes, they are found if you follow the link to Phil Bresnahan's paper, the MATLAB files are available at the Methods in Oceanography website.
Okay. Next question. Can you discuss best practices for collecting the validation samples and the best methods for determining pH in the lab on those samples?
Collecting the samples, I would recommend following the procedures outlined in Andrew Dixon's best practices documents for seawater CO2 measurements. Following that, taking the samples into the lab, a spectrophotometric pH measurement makes sense since we're working in the pH domain. Ideally, you would then measure an additional parameter, which could be dissolved inorganic carbon or total alkalinity. As far as I'm concerned, Andrew probably he may have a stronger opinion, but if you actually are able to measure the pH and or DIC and PC and alkalinity in your lab, you'd be in really good shape to perform quality control on a series of bottle samples alongside the sensor. I think at that point, we can all have our opinions about which parameters are better to measure, but I think that the differences are rapidly get swamped by spatiotemporal mismatch in bottle sampling. So probably the most important thing, in my opinion, and pay attention to when you're going to generate a data set like that is nailing down some sort of a sampling protocol to minimize spatiotemporal mismatch. And then, in addition to just trying to sample near your sensor in space, asking yourself the question, do I need to do temporal interpolation of these data in order to bring them into the best possible agreement with the sensor data point?
Next question for you, Todd, is if it takes 10 days to condition the electrode and then biofouling becomes an issue after approximately 35 days, how do you achieve continuous measurements?
Well, if you're thinking about the biofouling figure that I showed, that is one of the main driving forces behind developing the CFOX. So in a fouling environment with a passively flushed sensor, you can experience fouling in, say a month. You can 4 weeks in, you can start to, your data set has been compromised by fouling. First off, you would want to condition the sensor before deploying it always, which is one of the #1 recommendation. So don't deploy an unconditioned sensor. Second, address biofouling, right? So if you address biofouling, your sensors don't foul in 30 days, and we've shown that with CFOX sensors that operate on the order of a year.
Okay, and of course that ties into your recommendation of deploying 2 sensors. So when you start to see the biofouling cause a little bit of drift, you have the second one in the water that gives you the continuity.
Well, the 2 sensors alongside each other give information that's useful for quality control. It's not in the recommended protocols, but if you are trying to achieve a continuous time series, it is. I mean, I guess in my words, I'd say it's essential to have 2 sensors per site. So if you want that one site to have continuous measurements, you need a minimum of 2 sensors. One is in your lab ready to be deployed, and one is in the field making measurements.
So Todd, we have 2 biofouling questions. The first one is, what's the bigger biofouling problem? Is it actually biofouling on the sensor itself, or is it the biological activity that alters the chemical conditions located near the sensor?
Well, I don't know how to separate those 2 things. I mean, if you're talking about, is it the proximity on the order of a micron or a millimeter? Who cares? It's, either way, you have a fouling problem that has to be taken. It has to be removed. And what we've seen in some of these data sets that I've shown is that you can sometimes get away with doing a field cleaning of the sensor if you stay on top of the fouling enough. But sure, if you have fouling happening even in proximity of the sensor, near the intake, then you could be looking at a respiration signal that's local rather than the bulk seawater. So I think it is. I guess it's good to think in terms of am I looking at the signal generated by all the stuff growing on the mooring or whatever platform I'm deployed on, or am I actually looking at the bulk seawater? I mean, that's how I tend to think of it.
Okay. The next question, again, goes to biofouling, and we got it from 2 people. First off, how effective are the copper cages that you put around the sensor? And then the second is, where can you get them?
Well, the copper cage for the CFET, the Satlantic CFET is built by Satlantic, so they will give them to you. If you are talking about a Durafet sensor bought from a Honeywell distributor, I don't know that anyone sells any sort of a copper anti-fouling guard for that. That may be something you'd have to build in-house.
Okay, next question. What is the UVA analyzer that both you and Benoit mentioned?
So Honeywell sells a couple of different what they call analyzers that a Honeywell Durafet needs to plug into to operate. The UDA 2182 is the common one that they would sell you if you called up a Honeywell distributor, and its function is to power the Durafet and provide some data processing to give a pH output value. Both visually, there's an indicator on the front on a front panel, and it provides either an analog or a digital output for logging purposes.
Next questions were around if you store an instrument off-site or out of the water, you've indicated that you should keep it in water. What kind of water do you keep it in?
You could keep some sort of natural seawater or artificial seawater. Specifically for the CFET sensors with an external reference electrode, it's important to store them in natural or artificial seawater media containing bromide ion due to interaction of bromide with the external reference electrode. So there are some common mistakes that people have made with CFET sensors would be to condition them in natural seawater and then put them in a storage solution that does not contain bromide. So it would be not recommended to condition a sensor in natural seawater and then store it in, say, a tris buffer prepared without bromide.
Wonderful. And Todd, here's your last question, of which 3/4 of the people in the webinar stuck around to hear the answer to. Could you please give your thoughts on Benoit's NVS tris calibration procedure?
My feeling on that is that I probably would not recommend it, but it's hard to I'm not sure that it's a good idea to pass down harsh criticism on it when I'm not offering a calibration protocol for that system myself. So I don't know what that exact calibration protocol should be yet because no one has developed it. I haven't put in the effort to develop a UDA calibration. So I don't see any obviously wrong things with that procedure other than there is the potential there to make the to add in error to the calibration that might not actually be there in the first place. One issue with this is that you're talking about moving a sensor with a liquid junction in between solutions with vastly differing ionic strengths, which is not typically something that you'd recommend with any type of electrode, any type of sensor with liquid junction. You would want to condition it in a seawater type media and then leave it in that ionic strength, not moving it back and forth. So hopefully someone puts in the effort to come up with recommendations, because I know that there are many people out there using UDA analyzers. But off the cuff, what I would say is take the thing off the shelf, operate it with the UDA, take the number that comes out of it, and do post-processing corrections to it based on some bottle measurements.
Well, that's the last of the questions. Todd, thank you very much for sticking around. Thank you, Benoit, for the perspectives you added. For people who are interested, we had a number of questions as shown on the video right now. The presentation itself, as well as the underlying PDF, will both be made available on the CCAN website. The URL for that is on the slide right now. If you go to our next slide, please, what you'll see is that this was the first of what will be hopefully quarterly webinars for the next couple of years. And the next one is scheduled for May. We're still nailing down the final date, but that will be by Nina Benarczyk, and she'll be talking about pteropods as bioindicators for ocean acidification. So with that, thank you again to Todd, thank you again to Benoit, and especially thank you to Jen and the Ocean Acidification Program people at NOAA who helped make this possible. Take care, all.